This is problem 83 of Neetcode 150, Iceland and Treasure. It is also known as wall and gates on Leetcode. The problem is exactly the same. Okay, so let's read the problem together. You are given an m by n to the grid initialized with these three possible values. Okay, -1 is water. Okay, and you can't traverse water, so you don't have a canoe or a kayak. You cannot traverse water. Um, 0 is a treasure chest or a gate. Here it's a treasure. Infinity, they call it infinity, but actually it's going to be this value, right? This super long value. This is a land. Okay, so you're basically going to start in a land and you want to go as fast as possible to the treasure, right? And you don't want to go in the water. You don't have your swimsuit. So you're gonna have to fill each land cell with a distance up to its nearest treasure chest. If a land cannot reach the treasure chest, well, you're gonna have to keep its infinity value. All right. So we also have to assume that we can go up, down, right, left. We can go diagonally. So we have to modify the grid in place. We don't have to create another grid. Okay, that's cool. So um, let's use the React technique to solve this problem. Well, React is an acronym, and R stands for restate. So let's go ahead and restate the prompts in our own words. Okay, so I need to fill an M by hand grid, where zeros are treasures, -1s are waters, and infinity, aka large numbers, are basically a piece of length. For each piece of length, I need to find and update its values to be the shortest distance to the nearest treasure. Um, the movements are restricted to 4 directions: up, left, right, and down. And that's pretty much it. Okay, so we can take a look at this example. Well, it's hard to see, so you know what? Let's go ahead and check this example instead. So, also let me pick another color. So, perfect. So from this I, okay, I is for infinity, -1 is for water, and I draw them in blue so you can see them obviously. 0 is treasure, so I color them in yellow. So from this I, okay, so for this land, you can reach 2 treasure. You can reach one by going here. You can reach another one by going here. But notice that if you go up, you only have to move by 1 position to go to a treasure. So you're gonna be willing to go up, right? So this is gonna be equal to 1, and this value here also, right? You only have to move 1 case. You can go up by 2 cases to reach the upper treasure, but it won't be efficient. You only want to you can reach a treasure by moving only by 1 to the right. Okay. Same for this piece of land here. So you can go here, which is basically 2 case, or you can go here, which is going to be 1, 2, and 3. So we are well, it's easy to say this way, but for now let's just use let's just use this approach where we can without any code just say, okay, this is shorter, so let's add 2. Okay. Now for this piece of lens I, we can reach the treasure here. Notice that we have water here, so we can't really decode this. That's not something that is allowed in our case. So we're gonna go 1 down, and we're gonna reach a treasure. So we can write 1 here, and we're gonna have to render 2 here, because obviously we can only go down to reach a treasure. All right, so this was the example, so E in our React technique. Now let's speak about A, which is the approach. So notice that this is a classic multi-source breadth first search problem, okay? So what we're gonna do is that we're gonna start with a breadth first search for all the treasures simultaneously, and we are gonna find the shortest path for, well, for all the nearest piece of lands. Okay, so let me restate my words. We're gonna do a breadth first search. We're gonna start at all the treasures, and we are just gonna go around and see if there is a piece of lens. Okay. So on our first round of breadth first search, right? We're gonna add in the queue all these values here. So um, we're gonna add our this piece of land, we're gonna add this piece of land, and we're gonna add this piece of land. And after this first round, we are gonna set all these values to 1 because this is the distance that it took to reach all these nearest values. And we are gonna do the same thing for the second round, but this time we are gonna start at these piece of lands that we reach. Okay, so from this one, let me just pick purple for the second round. So for the second round, we're gonna go here, and we're gonna add this piece of lands. So notice that now we have a distance of 2. Here we are gonna add this one, right? Notice that we're gonna also test all the other values, but we're gonna see that we add either a treasure or a water, so these doesn't count. We're really gonna look for piece of lands. Okay, so here comes a potential problem. So let's look at this. Here we have our eye, and we can technically go up here. So we will potentially replace this value, which used to have a distance of 1. We might gonna change that to a value of 2, which is really not what we want. So to avoid this, we are gonna create a set of visited value. And if it is in the visited value, like if the value that we're targeting and potentially going to is in the set of visited value, we are not gonna go there. All right, so that's the code. That's a very broad overview. Now let's try to concretize this in actual code. So first, I will need something to ensure that the place I'm going to is actually inbound, right? Because we can potentially go somewhere that is not even in the board that we're given. So we have to, in order to do this, keep track of the rows and the columns. The rows will basically be equal to the length of the grid that we are given. And the length of the columns will be equal to the length of any column. To do so, let me pick the column at the first index. With that being said, we can now create our visit set. So visit is going to be equal to a set. And since we're using breadth first search, pardon me, we have to use a DQ. So we're going to create a Q variable that will hold a DQ. So just like this. So this is how we are going to handle each, like what I call this, the so-called rounds. Well, a round is basically going to be all the values inside this, right? So for every values that will be inside a DQ, go take a look at its neighbors. Go check if any of its neighbors is valid to be added in the queue back, and if it is, just add it in the queue. Okay, so now we can create the function that will, well, we can add a function that will add a cell to the DQ. This is something we know we have to do. So we're gonna say add cell, and we are likely gonna have to pass in the row and the columns. Okay, we can do the rest later. But what we know that we're gonna have to do is that we're gonna have to go for every row and for every column in every row. So we're gonna say for R in the range of the rows, and for C in the range of the calls. Okay, and for each of these, well, initially, this is the first thing that we're gonna do. Okay, so the add cell function is something we're gonna call later in our code, but the really first thing we want to do is add to our DQ all the treasures. So we're gonna go for every single cases in the board, and if the grid at this row and at this column appears to be a 0, I will add this to the DQ. So we're gonna say q dot append, and I'm gonna append to this. Well, it's coordinate, so it's row and it's columns. And I will also add this, by the way, on the visit. So visit dot add, since we have a set, and within this set we're gonna add the tuple row and columns. Okay, so now we are on a pretty good shape. So we now have a DQ with all the treasures coordinates in it, and we know that it is in our visit set. So we know that we have basically we kept a trace of where we went to, so we know that we're not gonna uh, create an infinite loop of I go to the land, I go back to the treasure, go to the land, go back to the treasure. So since it is in our visit set, we just want return there. Great. So now I will create a distance. Okay. And I will create a distance because basically for each rounds, okay, I will make sure that this specific rounds distance is going to be incremented by 1. Okay, so what I will do is that I will use a while loop while there is a queue, and while there is a queue, I will say for I in the range of the length of q. So we go through every single value, or on the first one, we're going to go for every single treasures. After this, we're going to go essentially for all the lands that we added in it. But for the first round, it's really just going through all the treasures that we added in our DQ. And we're gonna pop the left value. So we're gonna take her row and coordinate row and column values. So this will be done this way. And what we're gonna do on each round, we are gonna basically change that value at on the grid at this row, and we are gonna set this the value at this position on the grid equal to the distance. Okay, so initially all the treasures will be equal to 0, which is great because it's their current values and is also the distance you have to travel to go to the nearest treasure, as you're already in the case with the treasure. With that being said, the next thing is going to be to call our function add cell, and we're going to add our function add cell to basically to all its neighbors. So one neighbor is going to be to the right. Okay, so we can do this by calling column plus 1. Let me call this again. You can also go to the left, which is going to be simply calling columns minus 1. Okay, now we can go down, so we're going to increment rows by 1, or we can go up, which is going to be done by decrementing row by 1. Okay, so once these are set, let's actually create what is inside the add cell function. So inside the add cell function, well, this is where we want to add the cells inside the queue, or the queue, for the next round that we're gonna do here. So now notice that this first round is just gonna go over all the treasures. But after the first round, when we enter the second round, we are gonna go see all the neighbors of the piece of lands that is really like 1 cells away from the treasure. And we are gonna take these pieces or these lands that are 1 distance away from the treasure by first checking if it is valid. So it will be valid if we are in bounds. We will be in bounds if the C and the column and the row. So I can just take the minimum of both. If both are at greater or equal to 0, we will be in bound. Okay, so if this statement pulls or triggers a true value, well, it means that we're not in bounds. Okay, another case is that the row itself is greater or equal to rows. Okay, so this will mean that we are at an index that is out of bound. We're gonna do the exact same thing for the column. So if the column is greater or equal to calls, okay, what else can we think of? Well, what if we found a value that is already in visit? Okay, well, we don't want to go see this value because it already has a distance set to it that is definitely shorter than the one that we will add if we take that value and add it to the DQ. So we're gonna say RC in visit Or the last case is, what if we have a neighbor that is water, which is highly possible. So what if the grid at this row, at this column, is equal to -1? These are all the cases where we don't want to take this case because it is either out of bound, it is either something we already visited, or it is water. So in all these cases, we are going to return. Otherwise, it means that we found a land, and this land is probably well, starting from that land that we found, the treasure that we started from is definitely the shortest treasure we can think of, because otherwise another treasure will have found it before and would have placed it in the visit set before. Speaking of which, we are going to have to add in the visit. So we're going to say visit that had, and we're going to add the tuple row and columns. So we know we won't get back to this anymore. And we add the shortest distance to it at its value. We are going to say queue dot append. So we're going to add to the queue the rows and columns. And that's everything we have to do for the add cell, because we're not using recursion. We only want to add the nearest values if it is a land, so if it is not water, if it is in bound, and if it is not in visited. So that's everything we have to do. Okay, so see the flow here. We are going to start, and we're going to look for each rows, and then for each columns in each rows. And if we have 0, so if we have a treasure, we are going to add you in the queue, and we're going to add it to the visit set. Now we're going to go for every single value in the queue while there is a queue, and we are going to go see its neighbors. If it is a neighbor, and this logic if is here, so if it is neighbor and it passes this logic, we are going to add you in the queue. Okay, and it's in each round. Notice in each round of the value check in the queue, we are setting the grid at this position to the distance. So in order to be accurate, after each round, we are going to have to increment the distance by 1. So initially, all the treasures distance, or all the treasure cases, will be set to a value of 0. And now, after the first round, where we are taking the very next neighbors of each treasures, we are adding 1 to this distance. So we're gonna change their values to 1. And on the third round, we are gonna take all the nearest neighbors of these nearest neighbors of the treasures, and we are gonna make sure that their values is equal to the distance, which will by then be equal to 2. So this is how the algorithm works. Let's test this out. It works. Awesome. So with that being said, we have to go through every single rows and every single columns. So this is going to take us at worst a time complexity of big O of rows times columns, or m times n. And a space complexity also equals of m by hand, because in our DQ we potentially have to add every single values within the board that we are given. Okay, so thanks for watching. I hope you learned from this video, and I also hope to see you in the next one. Bye-bye.